Thank you, everybody, for go ahead and get started here. Other folks might be filtering in. Thanks everybody for being here in person. It's for those on Zoom that can't see the audience here, it's almost a packed room, which is a great testament to all the people supporting Lucas, which is always great to see. And thank you all for joining on Zoom as well for what is less of a, I don't like the word defense. I think it's more of a celebration of the hard work and time and energy that students have put into their theses. So for those that don't know me, I'm Drew Bennett. I've had the great pleasure of serving as Lucas's chair for his master's thesis and program. And so I'll just do a brief introduction and I'll turn it over to let Lucas take it away. And so I guess just to start, a little bit of background on Lucas. Grew up here in Laramie, so he's a fellow Laramigo where he was raised. But then he decided to leave and go out of state to Montana State University, where he earned a bachelor's of science in environmental studies with honors, graduating magna cum laude, which is very impressive, but also not surprising at all knowing Lucas. He also earned minors in GIS and cartography and Spanish, and studied abroad in Cusco, which is some cool experiences from that. He also then, after graduating, went on to earn a certificate in GIS here from University of Wyoming before enrolling in the Environment, Natural Resources, and Society Master's Program here in the Haupt School. He has a number of experiences that he completed prior to graduating from Montana State, including a couple of different stints with the Montana Conservation Corps, also served or worked for the Outdoor Rec program at MSU. But probably most relevant to the work that he's been doing and his career path that he wants to pursue. He worked for a summer as a land steward with the Mountain Area Land Trust in Evergreen, Colorado. And so he's really passionate about land conservation and wants to go into the land conservation field after graduating, and will have lots of opportunities there, no doubt. And so he really has this great through line and from experiences that he built prior to coming to UW. And then has continued to advance as he's been here at UW. In addition to the master's thesis that you're going to see today, he also developed a conservation planning tool for the Sheridan Community Land Trust as part of his practicum. That's a requirement for our graduate program here in the Haupt School, which if you have a chance to have Lucas share that with you, I mean, you'll just see the technical skills and capabilities that he has, just really fantastic geospatial abilities, and it's this really whiz-bang tool to be able to look at really cool ecological data, and was delivered to our partner there at the Land Trust, so they can incorporate that in some of how they make decisions around land conservation. So he has this incredible technical skill set that I feel so fortunate when I was recruiting for this position, this research opportunity. I think I vastly underestimated the skill set that it would take to actually pull this off. And in retrospect, if it wasn't Lucas in this position, I don't think that this project would have been a success. And so I really am amazed at everything he's been able to do, and just really thrilled to have had him on the team in the research group over the last couple of years. Couple of things I'll just share that I've learned about working with Lucas. If you want something done well and thoroughly, give it to Lucas, and you won't regret that. I think one of those things that you'll learn is that no good deeds go unpunished, and so when you do such high quality work, you'll keep getting more stuff dumped on you. So just keep that in mind. He's also, those of you that know him, he's very reserved. Can be an excellent listener, but when he speaks, unlike me, he has something really valuable to contribute to the conversation. So people listen. The other thing I've learned is never challenge him to a mountain bike race, because you will lose unless you're his dad. In which case, Lucas, because he has nothing to worry about. So I think what you'll see today is really the skill sets that he has. And I'm really excited for him to continue his career as he moves on from UW here in the near future. He's going to do great things in the land conservation community. And really excited to see everything that he'll accomplish in following his career going forward, wherever that path leads him. And so without further ado, I'll turn it over to Lucas. And just for those that aren't familiar with this process, Lucas will give about a 40-minute presentation And then we'll have 10, 15 minutes for questions and answers. And then we'll dismiss the public, and his committee will stick around and grill him for a bit of time afterwards. So, and for those of you on Zoom, there will be opportunities to ask questions as well. I'll make an announcement at the end of his presentation about how to do that. So,
Drew, are you sharing your screen?
yeah.
All right, well, thank you so much, Drew, for those words. And thank you everyone for being here today to hear about my thesis work titled Geospatial Mapping and Analysis of Surface Water Irrigation Rights in the Upper Green River Basin, Sublette County, Wyoming. Before I get into my work, I want to just quickly introduce the agenda for the presentation. I'll start with some general broad background and then some more specific background relevant to my work, and then get into the first chapter of my thesis, which is a little bit unique in that it's more of an applied project output where I create this novel data set in collaboration with conservation practitioners. And then I'll move on to chapter 2, which is more of a traditional academic research inquiry, but that relies on that data that I created in the first chapter. Then I'll make some concluding thoughts, and like Drew mentioned, we'll have time for questions. Water is the driving natural resource in the Western United States. It's the basis of all of our economies and ecosystems and dictates how we live our day-to-day lives. Climate change, however, is altering everything that we've known about how water works in the West. And this is marked by increased drought due to rising temperatures and changes in both precipitation, timing, and type. And when you couple that with changes in demand and increases in demand for water due to rising populations in the West, I think it's fair to say that water management has never been in a more difficult or precarious place, and the institutions that govern water in the West are being strained like never before. Changes that are going to occur due to these factors are going to impact economies and ecosystems across the Western US, and a lot of that change is going to have to occur in agriculture, which in many parts of the Western US accounts for up to 80% of water use in certain regions. And the changes that are going to take place in agriculture are going to have ripple effects across many different systems, both human and natural. It's going to become increasingly important to understand both the natural and institutional systems that govern and affect water in the West. With all that in mind, a great place to explore these sorts of issues is my study area, which is the Upper Green River Basin in Sublette County, Wyoming. And this study area is unique because it's situated in the nationally important Colorado River Basin, which is home to a significant amount of irrigated agriculture and whose water serves over 40 million people across 7 states and also Mexico. You can see in this map here on the right that there's a significant amount of irrigated land in my study area, and it's also home to the headwaters of the Green River, which is the largest tributary to the Colorado River, which eventually flows down to Mexico. A little bit more about my study area. I'm sure many of you have passed through or spent time up here. It's very rural and agricultural. And a lot of that agriculture is focused on growing grass hay, and to a much lesser extent alfalfa, but primarily for the purpose of livestock operations, especially cattle. And also unique about water use in this area is that for growing those crops, the vast majority of that is done through flood irrigation, which is an irrigation practice that's pretty much exactly what it sounds like, where water users will just divert water directly onto their fields and flood it several inches deep sometimes, as opposed to using things like sprinklers. And flood irrigation is typically considered a pretty inefficient use of water, especially in comparison to things like sprinklers, but it's also known to support some really important ecological processes, such as recharging groundwater, which then bolster late season in-stream flows and support wildlife habitat for migratory birds, ungulate species, and all kinds of other critters. All of the water that's used across this area for these irrigation practices is subject to Wyoming state water law, which is based around the doctrine of prior appropriation. And the doctrine of prior appropriation states that people or water users who divert water and put it to a beneficial use first have the right to use that water before anyone else who may come later. And it can be summed up by this common phrase, first in time, first in right. In the state of Wyoming, once you've diverted water, put it to a beneficial use, and have applied for a water right before you do that, then you then are granted a water right that becomes, in Wyoming, a property right tied to the lands where you're utilizing that water. Just to drive this point home a little bit further, this graphic on the left shows these three water uses along this stream: a municipality, an industrial site, and an irrigated field. And because the irrigated field has the most senior priority date, they put water to use in 1890, they have the right to use their water before these other two sources, even though they may be upstream on this particular system here. As I mentioned, the study area is also unique because it is part of the Colorado River Basin, which means that it's subject to a lot of other interstate water law and water governance. And there are many such agreements that govern water across the Colorado River Basin, but the most important is the Colorado River Compact of 1922, which is a water sharing agreement between the 7 states in the basin and also Mexico that allocates the water between the upper basin, shown here in purple, and the lower basin in orange, with each part of the basin receiving 7.5 million acre-feet of water each year. And an acre-foot, if you're not familiar, is the amount of water that it takes to cover 1 acre in 1 foot of water. Additionally, the upper basin, where much of the water originates in our high mountain snowpacks, cannot deliver less than 75 million acre-feet to the lower basin over any consecutive 10-year period. If there are violations under the compact, it could lead to what's called a compact call, where the lower base or the upper basin would be required to curtail water rights across the upper basin until the point that enough water was going downstream to fulfill the lower basin's allotment under the Colorado River Compact. And what's important to note for the rest of my project is that pre-compact water rights, so those with a priority date established under the doctrine of prior appropriation before the signing of the Colorado River Compact, would not be affected in such a curtailment scenario. So all of this is to say that there are a lot of really powerful institutional forces affecting water in this area. And because of these institutional forces, the water rights that people hold in this region are not necessarily all created equal. And people's ability to exercise their water right can be dependent on characteristics of that water right in relation to these institutions. So with that, I'll get into the first chapter of my research titled Water Rights Mapping for Conservation Planning. So as I mentioned, this first chapter is more of an applied project that I partook in with the Jackson Hole Land Trust. And JHLT is a small conservation organization based in Jackson, Wyoming, and their mission is to conserve private lands via the acquisition of conservation easements across the northwest part of the state. And in pursuit of this mission, historically, they haven't very thoroughly considered the water resources and especially the water rights that exist on these properties that they're working on. So the goals of this project are to change that by mapping water rights and pinpointing those areas that might have more important or potentially more resilient water rights in the face of such institutional forces. And the Land Trust is really keen on doing this because they're interested in conserving landscapes where the benefits of irrigated agriculture that I mentioned earlier, such as groundwater recharge and in-stream flows and wildlife habitat, where those exist on the landscape so that they continue. So the way that the Land Trust decided to tackle this desire to incorporate data about water rights into their mission was through their conservation planning process. And conservation planning is something that most land trusts and similar organizations will partake in to help set their priorities. We define as the systematic identification of lands that possess important environmental characteristics with the end goal of ensuring their protection from forces that would otherwise deteriorate or destroy them. In many cases, organizations will turn to GIS and geospatial technology to create their conservation planning frameworks. And this is certainly the case with the Jackson Hole Land Trust. We can see here that they incorporate these 4 data sets on the left: connectedness, resilience, and flow, which are all climate metrics, sage-grouse mesic habitat, riparian biodiversity, and big game migration corridors. Use that data to build this final prioritization model on the right, which essentially ranks the landscape, showing those areas that are most important to conserve based on their organizational goals and based on these four criteria on the left. The point of my project is to create a new data layer that meshes in with their current conservation planning framework that speaks to the resilience of water rights on the landscape, which again will inform this new version of a final prioritization model. And how this works in the GIS software is these data layers essentially just get stacked on top of each other like a sandwich, and each one has the landscape rated on a 0 to 100 scale, showing the 100 scores being the most important areas to conserve based on those various characteristics. And those output, again, this final prioritization model. So how did I create this water rights data layer? So I used data from this Wyoming State Engineer's Office, which is the state agency that governs water in the state, water and water rights. And they have a database online called the ePermit database that is really antiquated and difficult to work with, but nonetheless, it hosts all of the water rights data in the state. And the Wyoming Water Development Office has developed a geospatial conversion tool that takes the raw data from the state engineer's office, which is essentially just Excel files, and it converts that data into geospatial data that can be analyzed in GIS software. And after going through that process of downloading raw data and converting it to geospatial data, this is what it looks like. These green areas are all water rights, and in the state of Wyoming, water rights are applied for and mapped to quarter 40-acre sections. So the entire continental United States is divided into these 40-acre quarters, and water rights can be applied for on one or multiple of these quarter pieces of land, as defined by what's called the Public Land Survey System. At this point, I've mentioned the term resilience a few times, and how I defined resilience for the purposes of this project was the water rights predicted to be putting water onto the ground for irrigated agriculture into the future. And this definition, or I landed on this definition because it's really what the Jackson Hole Land Trust was interested in when thinking about this project and trying to incorporate this information into their conservation planning. So to think about resilience, I incorporated these three pieces of data, and these were determined through collaborations with some folks who work up in this region and deal a lot with water, irrigation, and water rights. And these three pieces of information were determined to be the most important and also the most practical to map and incorporate into this planning tool in order to create the final data layer. We'll go through each of these one by one. The first piece of data is priority date, which comes in that raw data downloaded from the state engineer's office. And I built a couple key priority dates into the tool. The first is November 24th, 1922, which is the day the Colorado River Compact was signed. And as you'll recall, if a water right has a priority date before the signing of the Colorado River Compact, it can't be curtailed under a curtailment scenario under that compact. Next couple of dates that I built in were March 1st, 1945 and March 1st, 1985, which both relate to state water law and the concept of irrigation seconds. So in the state of Wyoming, irrigation water rights are distributed on the basis of 1 cubic foot per second of water for every 70 acres that you're irrigating. But if your water right is before March 1st, 1945, you get what's called irrigation seconds, which is essentially a doubling of that permitted amount that you're allowed to divert onto your field. Get that water at the exclusion of everyone after March 1st, 1945, assuming there's enough water in the system. And if there is, then water rights between March 1st, 1945 and March 1st, 1985 are then also entitled to their irrigation seconds. These two dates are important in determining whether or not your water right essentially gets double the amount of water as a water right that doesn't fall within this range of priority dates. So I built that information into the water rights data layer that I created. And you can see how that plays out spatially here in this map on the right. you can see that the vast majority of water rights in the study area actually predate the Colorado River Compact and therefore receive a score of 100 to fit with the Jacksonville Land Trust's current 0 to 100 scale. And then the next bin of water rights or priority dates between compact and that second state, it's got a score of 75, and so on for the next bins. And the one thing that's important to note when looking at this map is that this only reflects the highest score in any given area. So in some cases, there may be water rights that are being masked by these high values here that still exist, but just aren't being displayed on this map. Next bit of information I incorporated into the resilience model was regulation, specifically the historic regulation of water rights by the State Engineer's Office since the year 2000. In case you aren't familiar with what regulation is, this is just a really simplified diagram to break that down. So imagine we're here on June 1st on this stream where 20 cubic feet a second per water are flowing down it. And there's an upstream irrigation ditch pulling off 7 cubic feet to satisfy these water rights on the left, and a downstream irrigation ditch pulling water to satisfy water right on the right. And there's enough water in the system that everyone can get their allotted amount. But if we move a couple months later, and now there's only 7 cubic feet flowing down this stream, if that first irrigation ditch is still pulling enough water to satisfy the water rights on the left, then there isn't enough left in the stream to satisfy this water right on the right, which has the most senior priority date on the stream system. So at this point, this water user would call up the State Engineer's Office and make a call for regulation, which would mean that the State Engineer's Office would come in and lower or shut off the head gate of that first irrigation ditch so that there was then enough water flowing downstream to satisfy the most senior water right. And the State Engineer's Office maintains records of every time that they do this, what streams they do it on, and also the depth of priority to which they have to regulate. So I could use that data and just go through the water rights layer that I built and get a pretty good estimation of how many times water rights have been regulated since the year 2000. Here, but again, most water rights are ranked as fairly resilient in this regard, with most still receiving the score of 100 because they hadn't been regulated in that time. And you can see some pretty obvious spatial trends where these streams down in the southwest part of the basin are called the Piney Creeks, and they are regulated the majority of years since 2000. Final metric that I built in was conveyance, which speaks to how far water actually has to travel down an irrigation ditch before it's used for its agricultural purpose. And this is important to think about because in some of these systems, if there's really long irrigation ditches and water is traveling a long way, sometimes or all the time, it'll be subject to conveyance losses, or water can seep into the ground and out of the irrigation ditch. And other times, if there's not enough water in these systems to begin with, it can be hard for water to actually make it all the way down a ditch to its field. So I calculated just a really simplistic straight line distance between each water right's point of diversion on a stream and its point of use where the water is actually being applied. And this is how that breaks down both spatially and in the scoring tool based on the scoring metrics. You can see that again, most water rights have fairly short conveyance distances. And these are generalized because they're just straight line distances, but most of those distances are less than 5 miles. When I put all of this information together and had those 3 scores based on the metrics in the middle, what I did is I just created a simple average of those 3 scores to create this final water rights resilience layer that I've been talking about now, which looks like this, and again speaks to the water rights that we predict might be putting water onto the ground for irrigated agriculture into the future. So there are a couple of deliverables for this project that for the Jacksonville Land Trust. The first is that final resilience layer that looks like this. You can see these dark blue areas are those that are ranked as more resilient, with the whiter and more red areas being less resilient based on those 3 criteria. And just to remind you, this is the data layer that's going to be incorporated into the Jacksonville Land Trust's conservation planning framework. Other deliverable is this raw data set that I built and that I created a web map for. where the land trust can essentially go into this, zoom around and click on individual water rights in areas that they might be interested in and see all kinds of information about it, like its water right number, priority date, how much water they're allowed to divert, and a bunch of other information like that. And this, particularly this tool here, there's a lot of interest in it coming from other stakeholders who work in the region, like the Game and Fish Department and other NGOs. So there's likely going to be some sort of public version of this tool that people can use to for water rights in this study area. To kind of wrap up chapter 1, I think that this is a really new and unique contribution to the land trust and also to the concept of conservation planning in general, especially thinking about these institutional forces like water rights and water law and interstate water compacts. It's something that not a lot of land trusts do, or other organizations that work in this sphere. And additionally, it creates a lot of opportunities for future work, both expanding this sort of thinking to other parts of the state, or even improving on it and thinking of new to display. With that, I want to move into the second chapter, titled Institutional and Environmental Analyses of Water Rights. And to recontextualize this chapter for all of you, again, this is the more traditional academic research inquiry, but again, using this raw water rights geospatial data layer that I created in chapter 1 to answer some more traditional academic research questions. And those 3 research focuses are, first, looking at the relationships that might exist between water rights characteristics and vegetation metrics on irrigated lands. Second, looking at relationships between a water rights irrigated lands and non-irrigated wetlands, again, using vegetation metrics. And third, thinking about impacts to water rights under potential curtailment scenarios under the Colorado River Compact. For the first 2 research focuses that use these vegetation metrics that I mentioned, I calculated 2 commonly used indices that speak to different aspects of vegetation condition. The first is Normalized Difference Vegetation Index, or NDVI, which is a measurement that quantifies vegetation health and photosynthetic capacity. And it's calculated as the ratio between reflected red light off of plants and reflected near infrared light off of plants, using this formula down in the bottom left. That formula outputs values between -1 and 1, with the logic behind NDVI being that healthy vegetation absorbs a lot of red light for photosynthesis and reflects a lot of near infrared light, so higher NDVI values represent healthier, greener, and denser vegetation. Second index that I calculated across the study area was Normalized Difference Moisture Index, or NDMI. This quantifies vegetation moisture content specifically by using the ratio between reflected near infrared light and reflected shortwave infrared light, using this formula here. And again, it outputs values between -1 and 1, with the logic behind NDMI being that vegetation with higher water content absorbs a lot of this shortwave infrared light and reflects a lot of near infrared light, meaning that higher NDMI values will represent wetter vegetation with lower levels of water stress. How did I create this NDVI and NDMI data? I used freely available Landsat imagery from the Landsat satellite program. And these satellites collect images across the surface of the Earth in various wavelengths of light every 16 days. So what I did is I set up my study design to calculate these indices during different parts of the irrigation season, being early season, mid-season, and late season, and also during different levels of drought severity, low drought, moderate drought, and high drought. And this allowed me to assess my research questions in these 9 different permutations of both season and drought that you can see laid out in this table on the right. And within each of those permutations, I randomly selected 5 dates from each scenario and calculated average NDVI and NDMI data sets across the study area for each scenario. After having done that, I could then extract these index values on only the landscapes that I was interested in for my research focuses and overlay the water rights data set that I created in the first chapter over these NDVI and NDMI data sets. So just as an example, what we're seeing here are these blue, white, and brown values are one of these NDVI data layers, specifically for the mid-season high drought stress scenario. And then I clip that data to only be on the landscapes that are directly irrigated. So for this water right here on the top, you can see its mean NDVI value in this season drought scenario is 0.31. And the mean NDVI value for this water right on the bottom in the same scenario is 0.26. Then did that across the study area for every water right, and then at that point I could examine the relationships that exist between water rights characteristics and these vegetation metrics on the irrigated lands served by these water rights. Those water rights characteristics that I examined were priority date, historical regulation, and conveyance distance, which you'll recognize as the three metrics that I used to develop the resilience model for the first chapter. To examine these relationships, I use simple linear regressions, and there's a lot to take in on this slide, so I'll kind of walk us through it quickly. On the x-axis of each of these plots is priority date converted to a numeric value, and then on the y-axis of all the plots is the NDVI value. And each point in each plot represents an individual water right, and each individual plot represents one of those 9 season drought scenarios. So for example, up in the top left is the early season low stress scenario with all the other early season scenarios across the top, mid-season, late season here on the bottom, ending in the late season high stress scenario in the bottom right. Speaking specifically to thinking about the relationship between priority date and vegetation condition, we might expect that more senior water rights would have higher NDVI values, especially in times of drought, or maybe later in the season when water is more scarce. That said, we can pretty clearly see in these plots that there are no strong linear relationships between a water rights priority date and NDVI values of the irrigated lands that are served by each water right. When we use the other metric, NDMI, we see the same lack of relationships. And the second water right characteristic that I examined was the history of regulation, which again shows not many strong relationships between these two variables, with the exception being these plots in the top right, which represent the early season high stress and mid-season high stress scenarios, where there are weak but not entirely negligible relationships, which indicates that there might be some sort of relationship between those water rights that are historically more regulated, having lower NDVI values, as opposed to those that face less regulation, having higher NDVI values. But again, when we examine NDMI, we don't see many, or we see few, if any, statistically meaningful relationships between NDMI water rights. And the final metric I examined was conveyance distance. And again, there are clearly not really any significant spatial or significant linear relationships between these variables. And the same can be said for normalized difference moisture index as well. To summarize this first research focus, there are clearly not very many strong relationships between water rights characteristics and these vegetation indices on irrigated lands across my study area. And one potential explanation of this could be that this region tends to be pretty flush with water for the most part. Along a lot of tributaries, people don't really have to worry that much about not receiving their water, meaning that they can irrigate more or less as they please. That's just one potential reason for these lack of relationships. That said, I do think that those relationships could become more pronounced in the future under further drought and water stress. That brings us to our second research focus, which again is the relationships between a water rights irrigated lands and non-irrigated wetlands. And to visualize what I mean by this, we can look at this water right down in the bottom right of this image here, bounded by the black line. And within this water right, we have irrigated lands in the bright green color, but also wetlands that are not necessarily directly irrigated for agricultural purposes, but that are still delineated wetlands. And those are what I mean by non-irrigated wetlands. So I used a really similar workflow for this research focus as compared to the first one that I just talked about, where I created these NDVI and NDMI data sets on irrigated lands and non-irrigated wetlands, and then calculated the average values of those indices water right. Again, I used linear regressions to examine potential relationships. And here we can see much clearer and more significant linear relationships, this time using the index values on irrigated lands as the explanatory variable on the x-axis, and the NDVI values of non-irrigated wetlands on the y-axis. See that in NDMI as well. And what these plots suggest is that irrigation, or the vegetation condition on irrigated lands, is closely related to the vegetation condition on non-irrigated wetlands, indicating potentially some sort of relationship between irrigation, or between irrigated lands and non-irrigated wetlands. To summarize, I think that this is a pretty clear, albeit expected, link between index values on irrigated lands and the non-irrigated wetlands within the same water right. This analysis really demonstrates the role that irrigation plays in supporting, especially the vegetation health on these wetlands. And while I think this is a pretty cool demonstration, it's also just a confirmation of a lot of previous work. In systems like these, some work has been done to show that the amount of water that arrives in non-irrigated wetlands can be up to 65% or more of that water is coming directly from some sort of irrigation practice. That brings us to my third and final research focus for this chapter, where I was really interested in examining what would happen to water rights and also the lands that depend on their use if curtailment was to occur under the Colorado River Compact. So in a compact curtailment scenario, what would happen is Wyoming would be required to cut its portion of water rights, or would be required to cut water rights across its portion of the Colorado River Basin, which is this area bounded by the blue line here. And how that would work is Wyoming would start with the most junior water rights and work backwards, cutting off water to rights until the point that enough water could be delivered downstream to satisfy the terms of the compact. And Wyoming's estimated exposure to curtailment across this entire blue bounded area here is between 30,000 and 80,000 acre feet. Yeah, again, just to note, that's across this entire portion of the Colorado River Basin that lays in Wyoming. The estimated consumptive use of water in my study area on average is 457,000 acre feet each year. And consumptive use is a really important concept. That is just thinking about the amount of water that's actually removed from a system, not necessarily the amount of water that's just diverted. Another important piece of information that I used in this research focus was knowing that the estimated annual consumptive use for growing grass hay in my study area, which again is the most common crop by a long shot up there, is 1.5 acre feet per acre. So with that information, I approximated the consumptive use of each water right in my study area based on irrigated lands data, which left me with the amount of consumptive use approximately that each water right uses in a year. And then I could calculate total amount of consumptive use across my study area, which again is this area in blue hashes here. And that was just over 225,000 acre feet, or about 49.3% of the total consumptive use across this entire area. Then I ran these three hypothetical curtailment scenarios based on Wyoming's expected or estimated exposure to curtailment. The first is the 30,000 acre foot scenario, which is kind of the minimum baseline expectation, where I estimate that 14,790 acre feet of water would have to be curtailed in my study area, which would affect 135 water rights, more or less, and go back to priority dates in 1960. Second scenario was 55,000 acre feet, which is right in the middle of that expected range of curtailment, where I estimate that just over 27,000 acre feet of savings would have to come from my study area, affecting 279 water rights and going back to priority dates in 1934. The third kind of worst case scenario of 80,000 acre feet, estimate that just under 40,000 acre feet of savings have to come from this study area, affecting 380 water rights going back to July 1923 priority dates. I was also really interested in the potential impacts to the landscapes that these water rights serve. So in the first scenario, it would be almost 10,000 acres of irrigated land impacted and almost 3,000 acres of non-irrigated wetlands. In the second scenario, almost double that. And then in the third scenario, over 26,000 acres of irrigated land and almost 8,500 acres of non-irrigated wetlands would be impacted. I say impacted because in curtailment scenarios, not all these lands would necessarily lose all of the water that is used to irrigate on them, because farmers and ranchers tend to have portfolios of water rights, and water rights can be manipulated and water can be moved from one place to another to some degree. So these lands wouldn't necessarily dry out entirely, but they would certainly face impacts due to these. So to summarize this last research focus, this analysis really does rely on some significant assumptions and generalizations. One of the big ones being that I didn't know the distribution of water right priority dates across the entire basin. So it could be possible that in the rest of the Colorado River Basin in Wyoming, there are much more junior water rights and a different proportion of savings or of consumptive use savings would come from those areas as opposed to my study area. And another big assumption that I made is that curtailment would only affect surface water irrigation rights, because that's the data layer that I made, where water savings could certainly come from other uses of water as well. Despite those assumptions, I think that this demonstrates a pretty unique proof of concept and a neat thought experiment into potential impacts of curtailment in Wyoming. And finally, I think it is kind of a cool way to visualize and think about the potential breadth of impacts for water rights and the landscapes that they serve. Wrap up chapter 2. I think again that all this work offers a pretty unique insight into the institutional forces that surround water use, irrigation, and wetlands. And it's a contribution to what is at this point a pretty limited pool of research. There's some work that's been done using this sort of data and asking these sorts of questions. But generally speaking, incorporating water rights and asking questions about water rights like this isn't all that common across the literature at this point. Finally, this work definitely opens up a lot of opportunity for new questions to be asked and more robust work to be done in the future. Some concluding thoughts I have is just to reiterate that water is one of the most important natural resources in the Western US, and that it faces a really uncertain future. Likely that the historical uses of water across the region and in the Colorado River Basin specifically will have to change to adapt to these realities. Those changes could result in massive shifts to the status quo, both for human communities who have deep cultural ties to the land and water, but also for the natural systems that are shaped by and dependent on these waters. Rising to meet these challenges is going to require huge efforts on the part of researchers, policymakers, water users, and other stakeholders. Part of their ability to face these changes will be to understand the institutional frameworks that govern water across the West. And I believe that this work represents a small but important contribution to this field that's only going to become more important as we all move downstream. With that, I want to take a couple minutes to acknowledge all of the amazing people who helped make this work possible. Thanks to all of my committee, Dr. Drew Bennett, Dr. Christy Hansen, Dr. Ginger Page, for meeting with me and contributing your insights. A big thanks to all these people listed here who I met with to fine-tune the conservation planning tool that I made for the Jackson Hole Land Trust. their expertise was really key in making it what I think is a pretty cool contribution. At the Jackson Hole Land Trust, I want to thank Max Luddington, the president, and Kerry Gold, the Green River Valley program director. I met with both of them a lot to think about these questions and about this project. And Max Luddington especially was really the visionary behind this. He's the one that had the idea to incorporate this sort of information into their work. And generally speaking, he's just a great guy and a really great visionary in the land trust community. It's an honor working with him. Also, a huge thank you to the McMillan Private Land Stewardship Program led by Drew Bennett and all of the amazing lab members that I'm lucky to have. Thank you all for just being very inspirational people. And Drew, I think I speak for all of us when I say that we really appreciate everything you do for us, and we hope you continue to do it well into the future, because you're really good at it. Thank you to my family, my dad, Peter, mom, Mary, and my sister, Becca, who all have interests that lie far outside of what I did here, but they've always been true inspirations for me. They've shown me how important it is to be passionate and hardworking and accomplish really cool things when you are both those things. So I love you guys. Thank you. Most importantly, thank you, Elizabeth. You are my best friend, and I love you so much. And yeah, you supported me in innumerable ways throughout all of this. And even more important than that, thank you to Lark and Gus, who make me laugh every day. Yeah. Thanks. Yes.
So with that, we have time, about 10 minutes or so for questions. People obviously in the room here can raise your hand, and I'll let Lucas facilitate those questions. For those online, feel free to raise your Zoom hand, and I'll call on you if you want to you can unmute yourself and ask your question directly to Lucas, or feel free to also type your question in the chat, and I can relay that to Lucas as well. So with that, open it up to questions that folks in the audience might have.
Question. Great work. That's really exciting to see, and I'm excited to maybe have the opportunity and to use this in the near future. Do you think that any of your findings from chapter 2, where you looked at the relationship between like vegetation quality, some of these metrics like conveyance distance, maybe for example, that weren't strongly correlated, were you curious to maybe like use that to inform your scoring as far as chapter 1's kind of conservation value metric?
Yeah, that's a good point. Yeah, it was kind of interesting to find that those water rights characteristics didn't necessarily contribute to the condition of vegetation, which made me wonder whether they were actually the right things to be considering in that model I built to speak to resilience for the land trust. But I didn't end up using any. To your question, I didn't end up using that information to inform those scoring metrics or the scoring criteria. But yeah, that's a good point.
Sorry. So if something has a good priority date score, a good conveyance score, but so you would expect that there would be good vegetation score. Is that fair, potentially, to say that? Or?
Yeah, that logically.
So, I mean, if there's a quarter that consistently underperforms on vegetation score, is that a reflection of operator error or operator indifference? Is that something that is useful to a conservation group, perhaps, that they might be able to say, well, you're not really using this or doing this, we can help, or
yeah, that's a good question. I think there could be many reasons that you might get a low or lower value of vegetation condition. A lot of that could be up to individual water users' choices, like they might be deciding to fallow one field for a year to I don't know the ins and outs of people's operations, but something that this work doesn't really consider is those sorts of individual choices that people make. But yeah, to your question, I think that that kind of information could be maybe something that conservation organizations would be interested in. And I even had conversations with those folks who are saying, or where they're thinking about the fact that maybe because an area is dry or ranked as less resilient, maybe that's a good reason to pursue conservation there. Not necessarily because it's conferring all these benefits through their water use, but because if agriculture isn't viable there, then maybe that would lead to it being sold and subdivided and developed. So yeah, I don't know if that answers your question. Emma?
Do you think the last thing you did in your second chapter where you were looking at if there was a curtailing of the taking of water rights for the lower basin, is that something that you think might be beneficial for farmers or ranchers if it was a public way to look at, you know, if there's a certain thing, how much of my water rights or whatnot would be taken? And then I guess, I don't know if there's, with that information, if farmers or ranchers knew, would there be any way for them to prepare for that? I guess in a year that might have.
Sure, yeah, good question. I don't know that that information should be like purposefully distributed, because I think it would scare a lot of people and probably make a lot of people mad, because people are really invested in water and tied to their water rights. And it being so based on so many assumptions, I don't know that I would actively go out and try and find people and say, look at this, your water rights might be in danger under curtailment. But to a certain degree, I think people already know that because people are aware of the water rights that they have and know their characteristics and are aware of these kind of things, because yeah, they're facing water challenges every day, and it's the most important thing to their operations. Yeah, it's certainly something that could be interesting.
Do you find that irrigated areas that were not growing grass hay or alfalfa had a different vegetation score often? And or did different crops have different vegetation scores?
Yeah, so I don't know which areas are growing which crops, so I didn't have that data. But that, yeah, that could be a good further step to look into. What I do know is that consumptive use across alfalfa and grass hay in this area is pretty much the same.
I know you explained this a little bit when the slide came up, but the scenarios where you have 3 scenarios and you have the curtailed amount of acre feet or of water amounts. You said that the non-irrigated wetlands would be impacted by the curtailing of the water, kind of at the same, maybe not the same rate, but comparably similar to irrigated lands. And I was wondering, if you're curtailing water, how would non-irrigated wetlands be impacted at the same rate?
It's a really good question, and not something I have a direct answer to, but it's definitely worth mentioning that these non-irrigated wetlands are affected by irrigation, as that water flows through fields and percolates into the groundwater and across the field and into those non-irrigated areas. But also if you're not irrigating because your water right got curtailed, that water is theoretically staying in the stream, which also is probably a pretty good thing for wetlands. Yeah, I guess I don't have a specific answer to your question, but yeah, the impacts on wetlands wouldn't necessarily be all negative or all positive, or due to the different ways that water can reach them and affects them.
Gotcha. That's like trying to separate surface from groundwater.
Yeah.
So sort of follow on that one. If there's curtailment, are the landowners apt to change how they do their irrigation? Will they move to sprinklers or things that are more efficient use of the water that would have an effect on wetlands as well?
It's a really good question, and there are probably people in the room that are better qualified to answer that than I am. But yeah, I'm sure people would have to change their practices and change the lands that they're working on, and yeah, I think that sort of thing could even incentivize the conversion from flood irrigation to more efficient water uses like sprinklers into the future. But specifically, I'm not too familiar with any individual operations to know what they would do, but other folks might be.
I think the jury's still slightly out on that. So the still needs a little more research, but the going literature shows that pivots tend to be more efficient, but they actually consume more water. The vegetation actually consumes more water. When so you're looking at consumptive use as your target versus diverted water, it's a trade-off that's still being investigated in terms of costs and effectiveness. And it really depends on so many factors, but it's a really good question. It's being investigated.
We're coming right up on the top of the hour, but if anybody has one last pressing question or anybody online, it's a quick one.
Can I ask a second?
Yeah.
Does it, so you were talking about the like seniority of water rights and, you know, so if a water right for a beneficial use was, you know, established in 1900 or an industrial use, you know, I'm thinking potentially maybe there's like some water rights for, you know, municipalities' industrial uses. If something like somebody like a land trust was interested in purchasing that and converting that beneficial use from industry to agriculture, does that change the date of that, the priority date?
So in my understanding, the priority date does stay. And as far as the technicalities of converting beneficial use in Wyoming, I'm not so sure. I think it might be challenging to do that. Would probably require some sort of legal or process. So I'm not entirely sure about the logistics of that, but yeah, feasibly, I think it is possible.
Well, join me in one last round of applause for coming out to support, and we'll wrap up and got some round of applause online here. So thank you all for joining online.